Hi, everyone. Welcome to Speakeasy JS, the JavaScript meetup for mad science, hacking, and experiments. I'm Feroz, and I'm your host this afternoon. So mad science is about building things that make people say, I didn't know that was possible. At Speakeasy JS, we like to feature weird and wacky experiments, not ready for production projects, and anything that is cool and interesting. So if you have a half-baked hack or something more polished that you'd like to share, just please send me a note and we'll get you featured on Speakeasy JS. And one more thing, if you're enjoying it every week, please help us spread the word and share it with people who you think would enjoy it. And with that, I would like to introduce our speakers for today. So today we're joined by none other than Karissa McKelvey, Marina Kukso, and James Halliday. So say hi, everybody.
Hello. Really happy to be here. I finally get to be on the other side of the screen instead of a lurker. So
nice. And Marina and James's video there was coming through. Nice. So I think we're going to probably go audio only for today because of the connection that James and Marina are using. So we'll go ahead. Let's go ahead and turn off our videos now, and you guys can share the slides, and we'll go ahead and get started. So while you do that, I will I just mentioned that Marina, James, and Karissa are part of something called Bits Co-op, which you should check out. The URL is bits.coop, and it's a group of it's a co-op for building cool things. It's an agency, and they build stuff that pushes the web platform forward. So it's all kinds of really cool web tech, WebGL, maps, peer-to-peer, data replication. And they built, basically, they are a co-op for building mad science stuff. So it's super cool. Check it out.
All right. Thanks, Feroz, for the intro. Hello. We're going to switch to screen here really fast, but we can just see our setup here.
All right.
All right.
Thank you for joining us.
Yep.
We're going to get started on the slides.
Okay, so for us, can you just confirm that you can see?
Yep, it's coming through perfectly.
Okay, great. All right, so today I'm going to talk about, along with Marina here, about our project that all of us on the co-op work on called Peermaps, which is a project to put maps in the browser using peer-to-peer technologies. And if you want to follow along, there's a link to the slides. I'm sure you can go to github.com/peermaps/talks and then just click, it's the markdown file. Okay, so suppose that you want to put a map in a web page. How are you going to do that? So there's a lot of options. Of course, you might be familiar with Google Maps or Mapbox, or there's a bunch of providers. You can roll your own kind of tile hosting, but that's pretty tricky and annoying, and I'll talk more about all of the ways in which that is a difficult thing to do. So first of all, let's talk about what a tile is. So if a map in a web page, that map is going to be loading for these things called tiles. So originally these tended to be files like JPEGs or PNGs, and then as you click and drag the map around, it would load different images based on what you're looking at a different zoom level. And then lately, in the past decade or so, most map tech works on a kind of vector tile. So that's more like an SVG kind of thing. Like Mapbox vector tiles are the most common in terms of tools that source from OpenStreetMap. And that's basically a kind of binary GeoJSON that's sort of SVG based, like it has move to instructions and integer coordinates. And then so you take those tiles and then they are consumed by a rendering engine, and that's ultimately what draws these things onto a screen. And that's usually going to be WebGL because that's sort of what you have in the browser to make things fast. So this really sucks, actually. Mostly because you need to get those tiles from somewhere. It's a great quote on the openstreetmap.org tile usage policy wiki page. OpenStreetMap data is free for everyone to use. Our tile servers are not. And so, if you just want to slap a map on a web page, you're going to have some troubles. The formats are also really difficult. They're not really designed around how graphics cards work. They're designed around other geospatial formats that have really evolved over time, and everything is kind of a mess, and it sucks. It's also very expensive. So this article that I link here is from 2018. Just to give you how much it costs to put a map in a web page, Google $7 for 1,000 map loads. So that's like a 7/10 of a cent every time somebody loads your web page. And Mapbox, this data is actually a little bit out of date. I just checked today on what Mapbox was charging. And over the free tier, which starts at 50,000, it's about $5 per 1,000 map views. So pretty similar to Google Maps. And I'm sure that most everything is about that price these days. So if you want to make a map, you're going to have to type in your payment information as the first step. And I don't think that's very fun. I don't think that's very nice. If you just want to make cool stuff, you shouldn't have to do that kind of thing. Also, because of the expense and because of all of the processing power to create tiles in this way, it just sort of naturally lends itself to centralization when you do things in this manner, because the compute jobs can take days or weeks. I was running, because this project is very old, so I think back in 2015 or so, maybe, I was running a batch job on my laptop in the desert, and took about a week, and my laptop kept overheating, so I had to actually wait until winter until I could run that batch job to process all of Planet OSM, just to give you some idea for the scale of the data that you're working with. Of course, you can spend a lot of money to buy a fancy computer to do this kind of stuff in Lin, but that's money, and that's like the whole problem that we're trying to get away from here, is typing in your payment information. Fuck that. These formats have a lot of problems with locality. You have the entire Planet OSM to do anything interesting with it, which kind of sucks, or you have to find a particular metro extract for an area that then you just have to depend on people doing that kind of work for you, and maybe they'll stop publishing metro extracts for the area that you're interested in, etc. You also need to update, whenever you update a part of a tile, you need to update the whole thing, which really doesn't work very well for these kinds of decentralized approaches. So what might an alternative to this state of affairs look like? So what we've built with Peermaps, our whole design is centered around not tiles. So instead we have a database, and that runs on your computer, like in the web browser, and that database can sync. And so the basic operation of a geospatial database like this is you can write records in batch mode. So you have batch insert and also deletes, and all of the features that intersect a bounding box. Those are the basic two operations with this approach. It's similar to tile in that you specify a bounding box and you get all of the results that are contained in that bounding box, but all of the records are kind of, they can stand on their own. They're not only lumped into that bounding box, and that has a lot of benefits that are kind of difficult to articulate, but that's how we've done things. Also, and then what you do from there is you have a list of the results from your bounding box query, and then you just can render them. So our formats are designed to be pretty easy to render with a pretty fast linear pass on the data, compared to things like Mapbox vector tiles where you have to do all of this stuff at runtime. It's much easier to deal with the formats that we're working with here. Another important consideration is that you can load the data in a sparse way from peers. So you don't need to have the whole data set in order to make use of it. That's very important as well. Ultimately, though, what we want to do is just fuck OpenStreetMap. We don't need that anymore. Responsible for all of the open map data. I don't think that's a very good state of affairs. And so one of the issues that we're trying to address with this is that you don't have like one kind of data set that does everything. And, maybe you have a lot of private or semi-private databases. You don't need a canonical data set for the whole world. And that's important for thinking about the relationship between centralization and plurality. I think I've heard in some, especially the SSB community, they have this idea of conceptual centralization, where maybe something is distributed on a peer-to-peer layer, but it's ultimately centralized in terms of like maybe there's a certain small group of people who control the protocol, or there's like a single namespace that's kind of tightly guarded, that sort of thing. So that's ultimately what we're designing around with this database. So let's just start with what the OpenStreetMap data format is like. And for that, you have to go all the way back in time to the 2000s when XML was very popular.
Oh, fun. XML, yeah. Let's get into it.
So in OSM, you have these three basic types of tags, or XML elements. You have nodes, ways, and relations. And also each of those has an ID, but those IDs exist in separate namespaces, which is very annoying. So many annoying things about this format. Just no limit on the annoyances. So here's an example of what a node might look like. So you have the useful parts, the longitude, the latitude, maybe an ID, also some other things. Maybe they're useful, maybe not, like a timestamp and who wrote it, that kind of thing. Then you have ways, which also have IDs, separate namespaces, attributes, and they refer with these things, where we have NDREF. Those link to nodes, their node ID, and you can also have tags. So the tags tell you important information like what sort of thing are we actually dealing with. In this case, this happens to be a residential street, which they use the convention for key is highway and the value is residential. And then it tells you where it came from in this other tag. But the tags are totally up. You can put whatever you want in tags. Finally, we have relations, which are similar to ways in that they refer to other elements by their ID. In this case, that's the ref field here. And they're sort of weird and janky. You typically specify this role property, which in the case of things like multi-polygons, where you have maybe, like you have a lake and it has some islands in it, that sort of thing. You have like inners and outers, and then you have to look up what these ways are by their ID. And then, the ways refer to nodes, but also relations can refer to other relations. Just a big old mess. Not very nice, because you have to basically have a database of all of this data. And likewise, you can have tags for relations. So this is even worse when you look at the format that you're most likely to encounter for dealing with OpenStreetMap data, OpenStreetMap protobuf files, OSM PBFs. So in the data, if you just start at the beginning and you go to the end, you're going to get all of the nodes, and then you're going to get all of the ways, and then you're going to get all of the relations in that file. And if that file is Planet OSM, it's 56 gigabytes. So you're going to have to process all of Planet OSM, like stuff all of the records into a key value store. And that's going to be an additional inflation in the size. And then you have to worry about like, well, how are you going to store those records in the file format? This is really bad for locality. So, if you have a way or a relation and you just want to see what is in it, you have to scan through the whole file, write it out to a database. It really sucks. So for our database, what we want to do is, again, be able to process parts of it without the whole data set and act on small chunks and just basically make it easy to render this data. Like make it so that it's not a giant engineering effort to build a rendering stack. So some of the components, some of the big components, there's a lot of little ones in the stack. We have the peer-to-peer geodatabase that's called Evros, which in Greek means interval because it's an interval database. So that's written in Rust, and we have it compiled to WebAssembly, and so you can also use it from JavaScript in Node and the browser, and it's on NPM as well. Then we have the ingest scripts. Those are the components that take Planet OSM and convert it into our various intermediate formats and then our ultimate format of the Evros database. Then we have the rendering stack, and that consumes that uses the database in the browser to pull up parts of the planet that you're interested in looking at graphically. And that's all in JavaScript, and it uses WebGL. So just to talk a little bit about the database, that's built on BKD trees and interval trees. So previously, I had done a lot of work on OSM P2P, which is a part of Mapeo, made by Digital Democracy. This is their backend that does peer-to-peer sync for their use cases, mostly working in the Amazon basin with indigenous groups to fight against, extractivism in the form of oil drilling or mining, that sort of thing. And then Evros is built, unlike that one, which is built on a Kappa architecture that does full replicas. Evros is really designed around having good patterns for sparse replication and an emphasis on the write performance and not just the read performance, because that's really important for these kind of architectures as well. There's the NPM package link and the Rust crate as well. So that's all working pretty good. There's obviously some room to improve on certain aspects, but I feel like it's functional. I've tested it up to past, I think, 100 million records, and Planet OSM is about 5 billion records. So that's only a 50-fold increase in the size. We'll see if it can manage that without more patches. So how this database works is that we have these things, BKD trees. They're really good for high batch write performance using this technique for log structured merges. If you're familiar with maybe how LevelDB works, it's similar to that. This is where you build small trees and you can, for example, increase the size of the trees in powers of 2 and kind of build a little binary counter that will, amortized over many operations, give you very good performance for writing large amounts of data at once. And then the other thing that this database draws on is interval trees, which let you have features that are not only points, which KD trees generally only give you points. Interval trees let you specify bounds. And if you extrapolate the technique of interval trees in multiple dimensions, then you can have things like rectangles or even cubes or hypercubes or that kind of stuff. Although in this case, this is all 2-dimensional, although the database works with arbitrary dimensions because it's easy to add that. So what's really nice about that, if you can imagine, the issue is that if you have a database that only works on points, suppose you have a really long highway. It's like you're in Kansas or Nebraska. The highway is very, very straight, and you're looking at a town that's along that highway, but there's no points for that highway when you're looking at the town. So if you're only querying for points, you're not going to see the highway that clips through the town. But with these kind of techniques, then you would see that feature because it's going to pop out through how the query traversals are done. And you also don't need to rely on, for example, doing polygon clipping to cut tiles, which is also really slow and annoying to work with. So the basics of how this database stores the files and the layout, how it does that is it, as much as possible, tries to write things out into pretty simple. And this is going to make it easier for us to put the content onto peer-to-peer networks. So initially, we're targeting IPFS and Hyperdrive. Although I would think that with the new changes to BitTorrent, I think there was a BEP that landed recently that lets you do some of the kinds of updates that you can do with IPFS and Hyperdrive on BitTorrent. So maybe we could add WebTorrent as well. That would be pretty cool. And basically, it's just a bunch of these tree files, and each of these trees whenever you have these kinds of B trees or whatever, you have a pivot point that you look to the left and the right. And then with a B tree, you typically have multiple pivots. So everything that intersects those pivots goes into one set, and then that could be subtrees or it can be inline nodes. And then you have nodes, which are everything that's between pivots. And you can also link to other tree files, and that's how the whole data format works. An important thing to note about the peer-to-peer database is that the write performance is a lot more important than it is in other use cases where you might have, a web front end to Postgres or something like that. In that kind of case, typically you see a lot more, like 1,000 more reads than writes, for example. But when you have a peer-to-peer database, especially one where you're doing device-to-device synchronization, write performance is really important because when you're syncing device to device, you're ingesting all of that data when you do that. So if that takes several minutes, it does with Mapase for some large data, then that is not very nice. And ultimately, we want to make something that can kind of scale to be Planet OSM sized, but also work in this sort of device-to-device way. And another thing still with is how to kind of get all of a Kappa architecture with these kind of sparse ideas. Architecture, really briefly, is a kind of design where you have an append-only log, and you build materialized views that answer questions about the log data in a fast way. And so we've been experimenting with peer queries and other sorts of models for how to make these kind of ideas work in our map use case. So ultimately, what we're building is having a planet scale OSM database that runs on edge devices without servers, and then doing the editing on the devices device to device without having to go through this single point of centralization, both in the infrastructure of OpenStreetMap and the kind of conceptual centralization of having an OpenStreetMap database. And a part of that too is if you update the database, the map should update. You shouldn't have to run a bunch of expensive batch processing on your device in order to see the map update. So what that looks like as far as the import data flow, this is ridiculous. It's like 1.4 terabytes to take Planet OSM as XML. And the protobuf is not as bad. It's only 56 gigabytes. But as you get the weekly change sets, they're in XML format, unfortunately, although they're quite a bit smaller than the whole database. But anyways, so you take Planet OSM and you take the weekly updates. We run it into the ingest, which we're still working on. That uses this GeoRender pack, which is our graphical format Marina is going to talk about a lot more in a moment. That gets written to the Evros, this geospatial database. Then once the database is written and distributed from the web, you can do queries on the database. It'll unpack the data and ultimately display what you see on the screen. So why did we choose to make our own map rendering pipeline as well as all of the peer-to-peer database stuff? For one thing, it's just really complicated and annoying to make custom visualizations for OSM data. I've tried to get all of that, Carto, Stack, like PostJS stuff running. It's just not fun. It's not nice. And the formats also for doing web maps are just really weird, and I just feel wrong about them. They feel off. I guess that's not a very good reason, but this is also a really great opportunity to make something that's really fast and simple, and so that you don't have to make a really complicated rendering engine for doing maps. You can just read the data and just stuff it into the GPU. Doesn't got to be very complicated. And you can also move a lot of those heuristic checks that are typically done at runtime, like about whether a relation or a way is an area or not, and like what the heck, all of the tags, like what you're supposed to do with that in terms of rendering. That's something that our format also lets you do. Okay, so now Marina's gonna take over from here.
Alrighty. So I'm gonna just talk a little bit about all the rendering stack. So just by way of introduction, if you're not familiar, everything that you see on your computer screen through the graphics card, otherwise known as the GPU or the graphics processing unit, things like, so if you want to display anything on the screen, things like a map, you can use something like SVG or Canvas. But really, what WebGL lets you write shaders, which is the type of program that runs directly on the graphics card. This makes it really fast. Programs like Canvas and SVG sort of are a bit of a ways removed from the graphics card itself. So we decided to go with WebGL, and we started with what the GPU wants, how it wants its data, the various things that it needs in order to work in the formats that it needs. So the first challenge that we came up against was the OSM data format itself. As James mentioned, like things like Planet OSM are really designed around providing single data dump in one big file, not really as much about designing toward the needs of the graphics card. So to provide the shaders with data in the format that they want, we pre-process the data into this sort of compact data format. And your pack is the NPM module takes one OSM entry and converts it into this compact data format for storing in the database.
And important, these are totally denormalized, so you don't have those references.
So here's just an example of the schema for one of the things, one of our sort of base primitives, I guess you could say. This is areas. This shows you sort of how it looks when it's in the buffer. And you can see the whole buffer schema at the link there. One of the main things to mention here, this is what goes into the database. This is the format that it goes in. And also, only data that's important for rendering is what gets converted. There's a lot of stuff, other stuff that comes with every OSM entry that we're not necessarily saving because we're trying to, this is specifically targeted toward the rendering engine. So some of the main transformations that happen on the data to prepare it for use by WebGL. The nodes, ways, and so first of all is the triangularization, coming up with the cells and the actual triangles from position data. Other software does this at runtime. This happens before it gets to the renderer. Another major issue is going from the nodes, ways, and relations, which are sort of the main categories of thing that you have in OpenStreetMap, to points, lines, and areas, which are closer to primitives in WebGL. So points corresponds to gl.points, areas corresponds to gl.triangles. And even though there is a line primitive in WebGL, it's actually really hard to do kind of fancy things with it. I don't know if you've ever tried to do things with WebGL lines. So in the lines, we use triangle strips with gl.triangle strips, which lets you do things like adjust width and do miter, various kinds of joins, make things look a little bit nicer. And then so points, lines, and areas are the sort of like the main three categories of things that we have in our buffer format. And then the last part of the main area is going from this collection of tags into one feature type, like amenity.library or office.government. And that one feature type is what determines the render style. And I'm going to talk about a little bit more of that later. And what all this means is that since these transformations happen as the data is being put into the database, once the data comes out, very little processing is necessary before the data gets passed to the shader. So that's kind of where you get these, we get like low single-digit milliseconds to go from database results to WebGL buffers. So returning back to this question of the feature types, in OpenStreetMap, every element, you have an entry for a road. It can have anywhere from 0 to many, many different kinds of tags. Some are important for rendering and some are not. So in this example, highway residential is important for rendering, but source digital globe is not. And you don't necessarily know which one it is. OpenStreetMap has an open tagging scheme, meaning that you can really give any kind of tag that you want, even though they have sort of tags that they recommend as a community that they've agreed on. But you can also have multiple tags on one item that can have matching styles. So just an issue that I came up with, I had a point that I was looking at that was both historic.castle and place.locality, which can both have a style associated with it. So which one do you choose? So the way we solve this issue is to come up with this sort of priority list, and this was hand curated, and the things basically as things are being transformed into going in this GeoRender pack, it looks at all the tags, and if there are multiple matches, it compares the priority, whichever is the higher priority, it matches with that. So here, for example, if you had something that was both land use dot whatever and power dot whatever, power is used for like power stations and power poles, it's more important to know that there's a power pole there than that it's land use agricultural. So this is something that also, if you want to, you can modify it yourself. And so where do we get the big list of features? What everything can be. There's the link. That's a nice big thing made up of many different subcategories for what type of thing it is. I believe our features JSON file has 1,241 types of things that something can be. Here are just a few examples. And shaders can't take strings as inputs, right? So you can't give it, tell it now you should be amenity.cafe. So in this features JSON, features are mapped to integers. So everything gets assigned of these integers. Whoops. So how do you set the style on something? So styles are per feature. So everything that's land use industrial or everything that's, whatever you want, you specify a style for that. There are, default styles for points, lines, and areas. So if you don't want to, you don't have to specify any styles at all. And we provide some sample styles that you can use. So in this example, you can see it's very similar to CSS in a lot of ways. It's kind of a flat JSON. So the keys are all features, and the values include many different things that you can set here. This is just the line stuff relating to highway.footway, which are like footpaths. So and one of the things that the style sheet supports is wildcards. So you can do highway.star and brace expansion. So you can do highway.footway and residential and trail if you want them all to have the same style. And also you can see, you can set styles specific to zooms. So, you don't necessarily want something to be 3 pixels wide at all zoom levels. Maybe when you're zoomed way the F out, you want it to be a little bit wider. So let's go ahead and show you this demo. So here the footpaths are Ukraine, center of town. And this is some parks, some lakes, and down here, let's see. Yes, these are actual individual trees, which is something that OpenStreetMap lets you map. So that's just an example. You could switch back. So how do you go from that JSON style sheet, get that data into the shader programs? And the way we do that is through textures. So there is a module called npm module called georender-style to PNG, which takes that big style sheet JSON and turns it into a PNG texture. And the texture is something that you can provide as input into the shader. It's a command line program, and you can see an example of the command here. I'll just show some up. And so next we're going to tell you this is what the actual PNG looks like this is for Kharkiv. So the way that the basic layout is, every column is one feature type. So that's what goes across the x-axis. So this PNG is 1241 pixels wide, okay, for every 1241 of those feature types. And then as you're going down, each pixel can hold 4 values, RGB, and A. So you can run each of those channels specifically in the shader. So for example, the very first pixel might have, I mean, I can tell you what it has. It has the color of a point, right? So the very first pixel will have the RGBA values of a point value, and the, I don't know the points, but that just gives you an example. And so you might have, for points, you might have 2 pixels worth, which would be 8 pieces of integer data. Is it integers or floats?
Well, it's hard to say actually, because it's a PNG file and those are integers, but then when it gets into WebGL, it's floats, but it's floats from integers, so you only have the range of values that an integer could encode, but in a float, because that's how graphics cards are.
It's a number. It's a number. So everything has to be converted into a number. So if you want to take, what should the style of the line be? Should it be solid, dot, or dash? That corresponds to 0, 1, or 2, etc. And because that data can be stored in a PNG, it turns into actual colors. So this is what you see here. And vertically, it goes through the 3 primitives, what points, lines, and areas are, what the different styles are, and for every zoom level. That's what lets you have different styles on different zoom levels. Okay. So yes, we talked about this. So then we have a GLSL, which is the language of shaders, GLSL specific module, GLSLify module, that can look up the style data from this PNG and convert it into some human readable text instead of D.0 bracket 1, etc. So you get things like line.fill color is an RGBA vec4, and you can use this to write your own shaders if you want, using the Peermaps style format. You don't have to use the shaders that come with our renderer. You can read the style data, use it to. Finally, the renderer itself is called Mixmap GeoRender. It uses Mixmap, which is a generic WebGL map viewer. And what happens is the GeoRender pack decoder, not the encoder, now the decoder, turns data that's in the Peermaps format into WebGL buffers that can then be passed to the shaders. It also reads the style, the texture, the PNG that we just showed you, using that GLSLify module. And it includes shaders that we've written, which are the GLSL programs that tell the GPU how to display geometry and what color every pixel should be. So that's sort of the main that go into the renderer that let you take the data from the database and display it on the screen. And we have some more stuff to show you.
Okay.
Oh.
Yep. So, well, there's one last part of this, which is how do you show like, little bits of text on the various features you want to show. This is a great quote from Wikipedia that I found. It's like it's in the first paragraph. Automatic text placement is one of the most difficult, complex, and time-consuming problems in map making and GIS. So one of the big problems is that if you show a piece of text, you don't want it to be at the same spot as another piece of text. So you have to kind of like have a physics engine and bump them apart, or just don't display one and display the other, or cycle through a bunch of combinations about where labels are allowed to be. And so I've been working on that lately, and I've got a little demo about it. So that's right here. So here you see there's a bunch of labels on the screen, including, so these are all points, and then there's this little river here, and this label, the river. And as you the demo,
Oh no.
everything is slow.
The X window or the window
Won't work, but that kind of ties everything together that we do have working. So we have the database working in JavaScript and Rust.
Also
pretty
lagged
good.
a lot when you lagged a lot when you were
Okay,
driving it.
yeah, I'll just close that one. Okay, cool. Thanks, Karissa. So we have the database working in JavaScript and Rust. We have the packing and unpacking into the graphics format, GRenderPack, that works in JavaScript and Rust. We have the style PNG stuff working in JavaScript, and we have Mixmap, which is just our WebGL map thingy. So we've got all of that working. What we don't have quite working yet is the ingest for all of Planet OSM, and especially working with continuous updates. So we're not quite there yet on processing the Planet OSM data. We also don't have style sheets for the text rendering yet. And, we need to do other stuff like seeding tools and sprites and whatever. But I can show you, hopefully this will work okay. So, well, before I do that, I can show you another demo here. This is of Alexandria in Egypt. And so what's cool is with our format, you can just pack as much data as you want into the browser. And so this is the entire city being rendered. I don't remember what the file size is off the top of my head, but you can just kind of see where that's at.
24 megabytes.
Yeah. So I have another demo here. Let me make the debugger a little bit bigger. Okay, so this demo is actually running Evros in the browser in memory, but that's because I didn't want to figure out how to delete stuff out of not quite IndexedDB, but the like mutable gecko file thingy, because I'm using Firefox, or there's a similar one for Chrome. I didn't want to have to deal with that. But what I do have here is this buffer on my website that I can import. And when I click the button, it's going to ingest that into the database, and we'll see some records here. Yeah, so it's doing a batch write, and it wrote into the storage. And then it does a query for the results. And this is all a lot slower because we're doing the screen share, but there we go. Okay. So this is a section of Vancouver in Canada. And you can see, and if I zoom out a little bit, so that was queried, that was written into the database and then queried out again. The real version will just do a query over the peer-to-peer archive instead. But you get a little taste that this stuff can be hooked up end to end. And I actually have a few of these buffers, so I can load the second one. I think it should be over here. So you see the batch write, and then it writes to storage. And now it does the query. The queries are much faster in Rust, so I need to figure out maybe there's something wrong with. Maybe like the WebAssembly to JavaScript bridge is the slow part here or something.
And where did you say that the data was coming from for that tile right now?
It's just a file that I put on my website. So it's loading that over HTTP. Yeah, there you see. And it's all stretched out because this is a cylindrical projection, and Vancouver has somewhat higher latitude than the other cities we were testing. Yes.
And you can set custom projections with this
Yeah,
system.
so one thing that's cool about our stack is that it's really easy to do custom projections. And in fact, I have some pretty old shader code that lets you take a proj4 string, which is a common GIS projection specification, and calculate that projection in the shader, which is, so that's another thing we want to do with this map stack, is just make everything as flexible as possible so you can do cool stuff like that. And you can, of course, click this link yourself, and it'll probably run a bit better than doing a screen share at the same time. Some pieces that we haven't quite started on yet, but we definitely want to make these, are an editor, especially with peer-to-peer collaboration, and seeding and hosting in ways that aren't public, but also maybe like semi-public stuff. Who knows? Routing and directions would be wonderful to have. I know Makola made a prototype a long time ago that I want to see how that works and see if we can integrate that into the stack. And then, mobile and filtering for zoomed out views and that kind of thing. These are all pieces that we just building toward these, but we have a lot of basic stuff to figure out still. So here's some links. Thanks. That's our talk.
Thank you.
Amazing. That was really good. Thanks so much for sharing that with us.
Thanks for having us.
Yeah, of course, totally. Super glad to have you. So I think I'll just say that was super impressive. I didn't know the extent to which you were kind of re-implementing everything, like using the data from OSM, but kind of redoing the whole stack in such a thorough way. So it was really cool to see you lay it all out like that, and to understand kind of the reasons why you did it and all that. And I love that part of your reason for redoing some of the parts was that the existing stuff felt off or wrong or gross in some ways. And I think that a lot of good software design comes down to artfulness and taste. And there's so much inertia with really old formats and stuff. So it's cool that you're rethinking this stuff.
Yeah, GIS land is just full of that kind of thinking. It's very conservative about formats and stuff, and it's just...
Well, also, it's if you can't even get the OSM Carto running, then what are you supposed to do?
Yeah, I think geodata is very special in its complications. So it's ripe for innovation, you could say. I think it's in an inflection point where our devices and mobile devices and computing devices, personal computing devices, are getting strong enough that we can offload more of the rendering to the device. So I think it's a good time to start experimenting with this kind of stuff.
Mm-hmm. Yeah, totally. Yeah, it seems like the old model of doing everything on the server, it just has too many costs, especially for certain use cases, the ones you've talked about. So it seems like someone just needs to kind of do the work to make it so that you can actually move some of the processing to the devices, and that's what you're doing. So I also thought the really tight rendering pipeline between the database and the WebGL side of things sounded really cool. It sounds also much easier to reason about the performance and the way that all works now that you've kind of re-implemented that. I'm wondering if you can feel that performance when you're using it. Does it feel faster than the existing stuff, or is there still more work to do for that?
Yeah, so for example, we can load entire cities in the browser, and for the graphics card, that's nothing. It's maybe a lot of cities might have 500,000, 1 million features. A graphics card can handle that kind of data, no problem. Graphics cards can render millions of triangles at 60 FPS, and with a map, you're not even doing a render loop like that, unless you're clicking and dragging. So.
Mm-hmm. Yeah, I also want to highlight, even if it was slightly slower, the point here is also that it's free, free and or cheap.
Yeah, maps are expensive.
Yeah. So if it's marginally slower, that's actually probably okay as long as it's still renderable, I think, because it would be free. Or at least as much, I mean, you could offload it to, hosts on S3 or something and make it not free, but very cheap.
Right. Yeah, that totally makes sense. Yeah, I mean, if the alternative is that you can't really deploy a map on your site or in your app because the starting cost just to even get started is so expensive, then yeah, I totally get it. But it's also cool that once you have the data locally, it seems like I mean, just my experience using something like Google Maps is that even on a really powerful computer, it really lags the whole computer, and focusing the search box and stuff, it just takes seconds. And I think having all the data there and never evicting it out of the cache is it just seems like you're starting from a place where you'll be able to get to really good performance that would even beat the centralized systems one day.
Yeah, another part of that too is if you think about what the usage patterns for maps look like, you're mostly, I mean, okay, so you live in an area, you're probably going to want maps of that area. It's probably not that much data, so it would make sense to have it around on your, and then it's just on your device. You don't have to do round trips to the internet to pull out more of it, except occasionally to check for updates. The other use case would be if you're traveling, if you're in a city where you might be in another country, you might not have a data plan. I've been in that boat plenty of times. And in that case, you absolutely want the maps on your device, because if you have no other way of getting data, you're going to get lost. So,
and actually, the tiles are, in a lot of ways, there's legal licensing restrictions on them. So you can, in theory, if you're a person who knows how to download them, you could just download them on your device, but you can't make a tool that downloads these tiles and uses them offline. If you start to get popular, they'll come after you for the tiles.
Right. Yeah. So if you're trying to put a map on your website today, and you you don't want to pay these people to run, you don't want to pay for their tile server, can you just take the data yourself and put it on your own server? Is that easy to do? Is that what people are currently doing?
I think then you have to pay for the tiles at some point. I guess you could do it. You would just have to not be popular. Because if you're too popular, they would be like, hey, those are our tiles. You owe us money for them. You can't redistribute their tiles, technically.
So is it the data that make up the tiles, or is it literally is it the data, or is it just the way that it looks?
I think it's the PNGs, literally the tiles themselves, or the raster tiles. They'll have a copyright on them.
Yeah.
Wow, I see.
If that's OSM data, then it's going to be the OSM license. I think Creative Commons something. But
yeah, the data itself is right. Yeah.
Yeah, if that's Google Maps or another map provider, those are all copyright, and then they sub-license their data from other companies, especially when it comes to aerial photography views, satellite imagery.
Right, that makes sense. Yeah. So what is the prior art on people taking OSM data and trying to has anyone tried to do something like Peermaps before, to make it more accessible and sync it over peer-to-peer networks and to make the format better for that? Or are you the first people and only people working on that?
No, I think there's been I don't know off the top of my head, but I'm pretty sure I've run into some kind of projects with smaller scope where they cut the tiles and then maybe put it on BitTorrent. But usually the problem is that these projects don't last for very long. So a big part of the design of this project is ideally making something that is sustainable. So that means making something where it's really cheap to run all of the batch processing, and eventually getting rid of that altogether, because that's a big part of sustainability too.
Mm-hmm.
Mm-hmm.
And maybe farming it out to other computers in like little cooperative computing clusters. Things like that, I think, are really important for the long-term health of these kind of projects.
Yeah. So how long have you been working on Peermaps for then? It's been a while, right? I feel like it's been ages that you guys have been working on it.
I was working on this stuff in like 2014, I think. And then I was working on some prototypes even before that, maybe in 2013. And I also was working a GIS job at university back in 2009. So, but that wasn't Peermap stuff. That was just kind of, other GIS mapping things.
Mm-hmm.
We have so many questions in the chat. It's kind of
yeah. Let's take some of those questions. Yeah, let's do that. So there was a question earlier from Tiny Fluff about how IPFS and Hyperdrive, since you mentioned you were using those or you were going to post the data to those networks. How do those networks handle lots of tiny files? Is that has that worked well for you?
Usually, libp2p will, which is the IPFS stack, will share every single file on the DHT, which if you have 10,000 files would be really bad. But I think that they were working on improving that, and or it's like configurable. We haven't gotten into the details of the networking, but hopefully it would be configurable for IPFS. Hyperdrive doesn't do that. It just announces the key, like the public key of the folder. So then we can, it won't announce for every single file, which I think would be better. But I think if, BitTorrent, I'd be interested in looking at BitTorrent, other ways of distributing it as well.
Yeah, just a few more comments I wanted to add to this topic. A long time ago, I believe in 2015 or maybe 2016, I actually had a really crude version of Peermaps cut onto IPFS and DAT. And yeah, it was the PlanetOSM protobuf format cut into 1 megabyte tiles, basically. And I think it was something like 200,000 files. And yeah, it took, with IPFS, I think it took like an hour and a half or 2 hours to just IPFS add that directory. Dat was actually quite a bit faster at that time, but I don't know what the stack is like right now. A lot of the design for the database especially is oriented around how these peer-to-peer options are not actually very good at doing things like Rabin fingerprinting or anything like that. So, for example, if you had something that was good at Rabin fingerprinting, you could have a lot bigger files in your database, because if you make a small change, you don't have to resend the whole thing, but we have to resend the whole thing with most of them. So that's kind of what it's designed around right now.
So we have a few more questions in the chat. Do you want to pick? Do any of you want to pick one that looks interesting to you?
Where is the chat button?
Oh, it's on the right side. Hopefully you can see it. If not,
I'll just. I don't know the older questions, but there's one newer one around non-authoritative naming. How can Peermaps support groups or organizations who publish their own naming of areas? So kind of the semi-private thing you were talking about before.
Their own naming of areas.
So if you want to have your own names for things.
Your own
like
names.
If you have your own map. So say
your own data.
I have my own map of this area.
Or almost like, I guess maybe one way to think of it would be like if you wanted to be able to rename something but not send it out to everybody, and then still be able to take updates for the rest of the map and kind of float your own patch of renamings on top or something.
Yeah, like if I had an organization or an app that had, for some reason, had a different data set than OpenStreetMap.
That's right.
Right. So I haven't been thinking too much about this, but I've been kind of thinking that some kind of Delta file system abstraction might be suitable for that sort of use case. Where that way you can always take in the underlying updates, but you sort of have a patch layer applied on top of it where you don't have to worry about merge conflicts or whatever, because it's just sort of additive.
Yeah.
I don't have a great answer for that though, but it would be really interesting to have that kind of a use case.
I think it would be possible now. It would be more ad hoc right now because there aren't good like high level libraries for Peermaps yet. But in theory, you could take the buffer schema format and make your own apps with it right now.
Yeah.
Right.
You guys, you'll have to pick questions for us. We can't really see the
I
questions.
don't know what to click to even see that.
Okay, all right. Yeah, let's see. I think there's a question here about Web Mercator and when the tyranny of Web Mercator will end.
The Mercator projection.
Yeah, so none of our stuff does Mercator at all because we can't be bothered. It's just a really simple cylindrical projection where you just divide it's nothing right now, but yeah, nothing about our stack is tied to any projection except the examples happen to use this crappy cylindrical projection. So you can use my GLSL module to do Proj4 if you want.
I think
I have a demo that it's on my website, substack.net. It's like one of the map ones, and you can just put the Proj4 string in the hash, and as you pan the map around, it updates the Proj4 string. So
yeah, I
that's
think what I'm excited about as far as like apps go is making like a directions app that hopefully wouldn't need Web Mercator or any like Mercator projection or anything, but you might imagine at some point needing some sort of way of rendering long distances. Yeah, to think about that.
Yeah. So one thing that I've seen that's kind of come into vogue lately is Mercator is used for really close-up stuff of streets because then you get right angles that are right angles. But as you zoom out, it does a linear interpolation to another projection that's better for like mid, like an Albros, and then like maybe even a globe as you zoom really far out.
Yeah, I've seen that on Google Maps. That's when my fans start spinning up as I zoom out.
So it probably won't end anytime soon, unfortunately. Sorry, basically the answer.
Karissa, do you want to pick the next question?
Oh, I can't scroll for some reason. I'm not sure, but I can only see the last question, which is where on the roadmap might you see heat map based JS styling overlaid on the underlying geodata?
I mean, you can. So the thing is with Mixmap, which is just a small wrapper around Regal, basically, you can put whatever overlays you want on that. It's not really a framework like a lot of the other map stacks. It's pretty much just here's like a big box of Legos that you can play with, and we happen to apply them loosely. Go ahead.
Isn't there a WebGL heat map based thing that Uber made? I forget the name of it, but you could probably, a lot of these things are built based on tiles, but if you made like an abstraction for the mix map that is plugged in, deck.gl, okay, you can make an abstraction around this that could plug into one of these existing libraries. You could like probably get something good, or at least that's like kind of functional without having to rewrite all of it. Because there's a lot of WebGL based stuff already out there for doing this.
Mm-hmm. Yeah, heat maps are also not super complicated, so you might be able to find like a GLS on.
So hopefully someone here will help us, and basically the roadmap is whenever you're ready.
Yeah, is there anything final you want to say to let people know, like what they can do to be helpful, or if they want to get involved, or anything like that you want to say before we go on to the next part of the event?
I don't know if we're really at the stage yet where we can take open contributors, but You can follow us on Twitter, and we post regular updates. You can also follow Bits Co-op on Twitter.
Yeah, I don't think we posted anything a long time ago. So
Yeah.
Yeah, I mean, I feel like soon we'll have a public channel when we get the first real demo out. I think we're really close. So I would just follow us online and then just stay tuned.
Cool. Nice.
GitHub, if you're on GitHub, follow the repos.
Cool.
yeah,
I'll
that's
put
probably the
URL.
best way. That's the actual feed.
I put the URL for Bits Co-op on the screen, and people can check that out. And I don't have the URL for the repo handy, but
It's just github.org.com/peermaps.
Okay, cool. I'll put that on the screen too. Cool. So I didn't check with you guys beforehand, but usually we do a social event at the end where we like meet the attendees and talk to them and stuff like that. And I was able to turn that into an audio only mode. So if you're down, we could go to that now, and it should work even without video now. It should just be like little 5-minute audio calls with the different attendees who are watching the stream right now, if you want to do that.
Sure.
Sounds good.
Okay,
Yeah.
Thank
cool.
you.
Let's do it.
Thanks.
Oh, I saw Sarah Path had a quick question. How do we finance the work? So we've been working down a big grant we got from Samsung Next on this project. We also have an open collective, but I don't think we've gotten too much more.
We got a small grant from Protocol Labs as well.
Yeah.
Yep.
So that involves integrating with IPFS.
Nice. So that's cool. Cool that there's financiers interested in this stuff too. Amazing. Cool. So we'll go to the social part now. So the way it works is you go to speakeasy.co/JS. That's the URL to type in. And when you get there, you'll just tap to start, and you'll get matched with a random attendee for a 5-minute chat. And this week it will be audio only. So that's how it works. And we'll go over there and hang out there for probably the next 20 to 30 minutes. And if you haven't tried it before yet, I know there's a lot of lurkers who like to just watch the stream. I recommend you try it out, and especially now that there's no video. So if you're shy, it should be a little bit easier to give it a shot. And there's also 3 speakers this week, so you have much higher odds of getting matched with one of the speakers. So cool. So we'll go do that now. And once again, thanks, Karissa, Marina, Substack. Really appreciate you coming here and sharing this with us.
Thanks, Ross, for having us. This is really great.
Thanks, Ross. Thanks, everyone, for listening.
Yep, no problem. All right, we'll see you all over there on the Speakeasy website. And also come back next week. We have another talk next week. It's always every Friday at the same time. So see y'all next week.